So today we're working with perpendicular lines. Quick review, my friends. What are perpendicular lines? Lines that intersect at what? Yeah, 4 right angles. Basically, remember when I asked you this the other day? Boy, highlighting pen is not the best one to make a point with. I asked what perpendicular lines were. All of you put your arms up so they were perfectly intersected like a cross, right? And it's because when they intersect, you get right angles. Do you guys remember the symbol we use for perpendicular? Yeah, I think some of you are showing me. I love the fact you guys are visual. It makes me happy. All right, yeah, the upside down capital T, right? 2 segments that are intersecting each other. So don't forget, I'm still going to be using that symbol a lot. So today is like taking twist of what we know about perpendicular lines and applying them. So a hint for tonight's homework. You got new theorems. Maybe use them on the homework. I know, earth-shattering. Like use it on the homework tonight. But a lot of these, if you did it, you just have to prove it a little bit longer. So the very first one is a definition that everyone should know based off of the name alone. All right, let's see if we can figure this definition out before I write it down. A perpendicular bisector of a line segment. Perpendicular bisector of a line segment. Basically, exactly correct. A line that will intersect a line segment. Where's it going to intersect a line segment at? Yeah, so back in the midpoint, right? So I get the 2 congruent segments, and it's going to form a right angle in the process. So it's just multitasking. It's just a line that's going to be multitasking, but that's basically its definition. So I got to make sure I do it the same as the other class. So give me a moment to open up my notes. My luck is I would do it 2 different ways and then try to quiz you over it. I've done that before. It's not really fair. Some of you are like, oh, it doesn't matter. All right, pretty easy. Definition is just a line, perpendicular, and you can use the symbol if you want, to a segment at the segment's midpoint. So if I ever tell you that you have a perpendicular bisector, you automatically would give me 2 things. 2 congruent segments, and you give me right angles. Make sense? So it just is really combining 2 of them together. All right, so what would be an example of this? Something simple as this. We'd have like if line AB is perpendicular, 1 second, no, this is not what I wanted. I want it to be a line. Line AB is the perpendicular bisector of segment ST. Now, what should that look like if we're doing it? Well, you have to have segment ST. That's not going to change. Where's line AB going to do? Yeah, cut right through the middle and cut at a right angle, correct? So what should be drawn in there? Oh, actually, I probably should put my labels down. Yeah, I'm going to have my 2 congruent segments, so I'm going to make my segments congruent, and I have to show what type of angle. Yeah, so I want to show my right angle as well. So the moment you have a perpendicular bisector, you mark your 2 congruent segments and you mark your right angle. A lot of times if you ever do that on a proof, you're going to probably use both of those pieces of information. So use that to your advantage. All right, another thing that we need to talk about is some terminology and just understandings that we use in geometry. A lot of times we talk about the shortest segment from a point to a line is the perpendicular segment to the line. So here's what I'm talking about. Here's line L. Here's point P. If I was to draw a line segment from that point P to line L, what's going to be the shortest one? The one goes straight down, right, to the line. So that's always, that line segment we just drew in is always the shortest one. Think about it. If I went over here at a tilt, is that going to be shorter? No, think, guys. What type of triangle did I just form there? What's the longest part of a right triangle? So obviously the hypotenuse is going to be longer. The only way that I'd get around that is if I go straight down. Now, even if your line is slanted, and let's say your point is over here, the shortest distance, the shortest line segment from that point to that line is still going to be the one that makes a right angle with it. We talk about the perpendicular distance or the distance from a point to a line. and it's always going to be the length of that segment. So let's put that down. The fact is used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. And I use that with you all the way through second semester, especially when we talk about circles and angles. Because we'll talk about there's a point just floating in the middle of an angle. How do I get to the side? I'll always draw the perpendicular line. So it's little things like that. So it's huge that we do this. So let's think about this for a moment. On example 1, it says name the shortest segment from point A to segment BC. So in that diagram, I'm looking at point A. Guys, which one of my 3 segments is the shortest? Yeah, so first thing we know, segment AP is going to be the shortest one. Wonderful. Now it says on here, write and solve an inequality for X. So I want to figure out a general idea of what X possibly could be. Well, what did you guys tell me earlier about segment AC? It's the longest one. It's the hypotenuse of a right triangle, right? So I know the hypotenuse of that triangle. Let's do it this way a little bit first. We know that segment AC is going to be greater than the length of segment AP. Notice the segment bars went off because I'm talking about inequality. I'm talking about length. Now, that's not the inequality I want. I want some algebra, people. I'm going to write this instead. X minus 8 is going to be greater than 12. So what does that mean? X has to be greater than? Yeah, it's just going to be greater than 20. So that's what I want for that question. Name the segment that's going to be the shortest, give me the inequality, and solve for it. Easy, right? So what's on the next one? Example 2. What is the shortest segment from point J to line GI? Yeah, so segment JH, right? Could I say segment HJ? Would we be okay with that too? Yeah. Yeah. And then we also know again, oh yeah, this one's like the hypotenuse of that right triangle. Obviously, it's the longer segment. So I know that IJ is greater than HJ. So can I just go X plus 4 is greater than 11? X has to be greater than what? So those are the parts that they want. Easy? That should be just fun little short algebra. I hope it is. All right, now we get our theorems, which I know you're just all dying for, and then you're just living to have these. All right, notice, do you see a name for this first one? No. Which means if you actually use it in a proof, what do you have to do? Write it out. I know. Oh, whine. Okay, anyway, let's go on with this one. It says, if 2 intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. Now guys, did we have anything before about linear pair of angles being congruent? Didn't we have a theorem, it was probably last chapter, that said if 2 angles of a linear pair are congruent, we knew that they were right angles? No, the linear pair theorem says they're supplementary. I can't remember that. Yeah. Because the fact is, if they're congruent to each other and they're supplementary, don't they both have to be right angles? So if that's a right angle, doesn't that make my line segments perpendicular to each other? So really, this is just a step farther in that thinking. So because we know if that's a linear pair, they both had to be right angles in order for that to even happen, for them to be congruent. So you can write it as a conditional statement if you want. It's not that great, it doesn't really help too much, but it says if 2 intersecting lines form a linear pair of congruent angles, and you can just use symbols, then lines are perpendicular. Just a slight abbreviation. I don't know if that really would help. To me, like the longer version might be helpful, but it gives us a way of doing that. This one to me, like, you could show this algebraically pretty easy. Now the next one has a theorem, so do you think it might be helpful? What do you guys think? Guys, look what's given to you in that original diagram. Let's see if we can kind of come up with the proof ourselves a little bit. What's marked on that original diagram? A right angle, right? What else is there? The parallel lines. So I'm going to have parallel lines for this to happen, and I have to have a right angle. Wait, If two lines intersect at a right angle, they're what to each other? Perpendicular. Okay, so here's the thing. If that's a right angle, what does this angle down here have to be? Because they're what type of angles? They're corresponding angles. And if I have parallel lines, corresponding angles are congruent. So that means I'd have to have a right angle. So doesn't that make line Q and line P also perpendicular? That's basically what that theorem just showed. Okay, we're going to do that. For us, we're like, oh yeah, that naturally flows. We didn't write a formal proof for it, but you can see how it works. But here's the actual formal theorem for this, and this is huge. First of all, it has to be in a plane. These have to be coplanar lines or this will not work. If a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So in this one, what we started with is the fact that we knew that Q and N are perpendicular as a natural result, and because we know how to do the math, the corresponding angles are both 90 degrees. We know the other one's automatically here. Now, guys, look at the pins in my hand just a little bit. All right, can the green pin be our transversal? Are you guys with me on that? Can I have a line going this way, so everyone sees perpendicular, and one going this way? Are they still perpendicular to the green pin? Now remember, I need them to be in the same plane. Are they in the same plane? No. So are those two lines parallel? They're actually what? Skewed. So that's why we have to change the rule and say, hey, guess what? These both have to be perpendicular for it to be perpendicular. Does that make sense? That's why they say in a what? Plane. That's why they do that. Because I can show up skew lines with this. It'd be a little bit different. All right, let's do another one, our last theorem, and then we just get apply stuff. I'm sure you're just living for the joyful moment of this. All right, so the next one. If two, guess what type of lines? Coplanar. If two coplanar lines are perpendicular, you could use the perpendicular symbol if you don't want to write this all out, guys. To the same line, then the two lines are parallel to each other. Again, think common sense on this for a moment. We know the definition of perpendicular lines are that they intersect at what type of angles? Right angles. So basically, if you were doing this one, the first thing you would mark would be right angle here, right angle here. What would be the next thing you would tell me? Oh wait, all right angles are what? Congruent. Well, aren't they also corresponding angles? So if corresponding angles congruent, my lines had to be what? Common sense proof. But it really is, in some way, I kind of like, this is kind of like the transitive property of parallel lines. It's like if I have two that are perpendicular to the same one, I can go, they're parallel to each other. We can't say perpendicular, 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 but isn't that kind of the idea behind it? So let's write the short version down. All right, so if two lines perpendicular to the same line, then lines are parallel. So just shorten it up a little bit. The one word I probably should put in there, and I'm being a little slack, is the fact that they have to be perpendicular to each other. Yes, sir?
Isn't it kind of like the transitive property?
Totally.
An S and S and T is R and S.
Yeah, the only problem is the symbols change. But it's kind of the idea, right? Because we can't say they're like, obviously, R and S are not going to be perpendicular to each other, but because they're both perpendicular to the same one, I wish we could say like a congruent perpendiculars theorem. You know, it's kind of like the congruent supplements theorem, but I think transitive property is a better way of describing it. To me, it's kind of transitive. I call it the transitive property of parallel lines. There is absolutely no name, and I know I'm being very incorrect. I'm sure a mathematician in college would be cringing right now, but he's not here. All right. So as long as you understand how it goes together, I think we're good. All right, let's keep going because I want to see if we can get through as much of this as possible. The last class I didn't get through the proof, and I want to get there for you guys. All right, first things first. I think even if we didn't have today's notes, I have a feeling you'd be fine on this first problem. It says solve to find x and y in the diagram. What would you guys do? You said set them equal to each other. Do I want to set them equal to each other right away? Because they are. But do I want to set them equal right away? Do anyone see a problem with doing that first? There's two variables. Right? No, darn it. I don't want to do that yet. So is there something else I could do? But that's not a bad idea because sometimes that's what we do, right? What do you do? Tavis. Which two could we add together to equal 180? Which two? There's multiple angles here. So these two here, or the 10x, you could do that, but I still wouldn't get rid of the y. Think harder. Oh, what did I hear? Do what? Yeah, equal 90, right? I mean, sometimes life is easier, okay, right, than what we think. Because think about it, linear pair, if one's a right angle, what's the other one have to be? Yeah, so we know 10x is equal to 90. Didn't this just take away that whole worry now about having two variables? Because now that I get x is equal to 9, can I use what I know? Which we do that, know that equals 90, right? 8x plus 4y is equal to 90. Because if one's a right angle, what does the other one have to be? A right angle. The cool thing is all I have to do is substitute 9 in for this. So I get 72 plus 4y is equal to 90. 4y should equal what, my friends? 18. Now, I need to chew you guys out just a little bit. I was looking over your systems of equations worksheet, which, once again, I gave you the answer key for. Lots of people gave me decimals for answers. Do I like decimals for answers? Guys, you got to learn how to work with fractions. That became 18 over 4, which reduces down to what? Why change it even to 4.5? Just leave it as 9 over 2. As long as it's in simplest form, you're done. It's okay. I did not ask you to change it to 4.5. That's just more work than what you have to do. Just give it me a fraction in simplest form. That happened a lot because some of you rounded when you couldn't. Like divide by 1/3. When do I stop putting the 0.3? You know, like 0.3333. Where do I stop? You can't. Leave it as a fraction. You don't have to worry about rounding. So use that to your advantage. All right, ready? Let's do a proof. All right, now a lot of you are catching on. Notice how the book and like worksheets will a lot of times not put the word line in front, which you know drives me crazy for improper notation. You still do the right thing. So like if you're working on this one and it says R is parallel to S, you need to tell me line R is parallel to line S. And my S's have a weird curly Q at the end because they look too much like my 5s. And then that's going to be given. Now remember, my goal is to show that line R is perpendicular to 9T. So I need a right angle there. That's my goal. So work with me a little bit on this first. The first given tells me line R is parallel to line S. What do I know? Are you guys in agreement or disagreement with Gorman? I got two corresponding angles. Exactly. What do I know about them? Congruent. Awesome. I love it. So let's say that then. Angle 2 is congruent to angle 3. Why? If parallel lines, corresponding angles are congruent. Now, could you say corresponding angles postulate? Yes. That is also the same. How did I know to start with the parallel lines? Well, what was the step before? Parallel lines. Okay, that's a good start. Notice I marked it. I should mark it congruency, though. A little bit better idea. Nope. Because I started with what first? What was before? Step before was what? Parallel lines. So I used the fact these were parallel in order to come up they were congruent. If it's flipped is when I start with the angles to get the lines. I started with the fact they're parallel. All right, I'm stuck. What do I do next? Evan, what do I do next? Yes.
What is the difference? Wait, why is the corresponding angles a postulate? Why are the other three?
Remember, the postulate was unprovable, but we can use the postulate to prove the other three.
Okay.
Yep, that's why. Nope, that was a good question. Yeah, Jason, what do I do next? Yes, thank you very much. Now, guys, hopefully we're getting to the point where you see this right away. Yep, now we get the transitive property. Excellent. Are you guys starting to see how the transitive property really helps us? Yeah, especially when we were talking about congruencies of things. So then I get angle 1 is congruent to angle 3. That's the transitive property. It's not substitution because it's a congruency sign. So, all right, now look what I have marked here. I got angle 1 is congruent to angle 3. Now, guys, you stay there. I'm going to scroll back. Oops, too far scrolled. Look at the very first one. If two intersecting lines form a linear pair of congruent angles, then the lines are what? Perpendicular. All right, so the only thing we have to still mention, so everyone's happy in this theorem, is the fact I have a linear pair. Well, scholars, do I have a linear pair? All right, so let's just write that down so we have everything perfectly fulfilled in our hypothesis of this. So the only thing we have to sit there and say is angle 1 and angle 3 are a linear pair. No, a linear pair. We know that they're supplementary too, but we don't need to say that this time. And that's just definition of a linear pair. Where in the world did I get that from? Isn't that just from my diagram? Given in my diagram? So now we're at our very therefore step. I know that line R is perpendicular to line T because of that very first theorem. It says the following: two intersecting lines form a linear pair of congruent angles, then I get perpendicular lines. Now, another thing you could do, if you showed me that angle 1 and angle 3 are a linear pair, didn't we have a theorem that said the angles are right angles? If you did that and then said the lines are perpendicular by definition of perpendicular lines, it's the same way of doing that proof. I just used the theorem that we've just had today. Don't forget to use what you've had recently. All right, let's keep going. Let's have some more fun. Peter, did I just say there was another way of doing it? Okay, moving on. We don't have time to go a different way. Sorry. But I did agree that there's more than one way of doing that proof. All right, this one says find the value of x for which line L is parallel to line M. All right, here's the difference. They're not parallel, but I want them to be what? I want them to be parallel. So how do I treat them? Like they're parallel. So basically solve for x, please, okay? If I want them to be parallel, I kind of have to treat it like they're parallel in order to solve for the right values. So if I want these two to be parallel, don't I need my corresponding angles to be congruent? So sometimes it's meant to be as easy as it looks. Whew, tons of work to show on that one. Hi. Using the same idea for B. If I want them to be parallel, what does x have to be? Well, what type of angles are those two angles? So they need to be what? I think that's a 95, right? They need to be congruent. If I want them to be parallel, I need the angles to be congruent. So we treat them that way. So I get 2x minus 5 is equal to 95. And you guys all know it's not going to stay that easy, but at least it's fun to start with. Show a little bit of work, my friends. Okay, now let's have fun. Number 5. Find the value of x and y. This is where a lot of you also go, there's just so much stuff. It's not simple like the last one. And instead of just sitting there and chilling for a moment, I was waiting for it to go over. All right. Why not sit there and go, oh, it might be multiple steps. Oh, well, here's what you know. Because what's one thing I know right away? Yeah, I have line J is parallel to segment AB. So basically, in my head, is there anything illegal, or even on our paper, to extending that? No. Is there anything wrong with just making it so my transversals look like transversals? Now start talking to me. What do you know? All right, 2x. Yep, one thing we do know. I completely agree. Do you guys agree with me? I have a pair of alternate interior angles that are congruent. So I got 2x is equal to 5y. Okay, now in your head, I got one equation with two variables. Do I probably need another equation with two variables? Okay. Do I have another one anywhere? Brooke, what do you think?
Oh, wait, never mind.
Yeah. What?
5y's equal to 1.
No, the whole thing would be, that would have been helpful, but actually you don't have to do that. Here's my question for you. Can this be a transversal? And this be a parallel line, and this be a parallel line, right? Look at the angles that I'm marking, my friends. Well, what are those called? If they make an F shape. I have a pair of corresponding angles that are congruent. Notice, probably if I did this, you probably would have seen it quicker. But you have to learn to go like, oh, I can ignore that other line coming down from him? Yep. You just got to look at 2 lines and 1 transversal. So I also know that x minus y is equal to 30. Now, if you look at my notes online, you're going to see me use elimination. Guess what I'm going to use instead to solve this one? Substitution. But notice, I don't care which way. Just get it. Okay? Substitution or elimination here. I think it's easy just to change this one over to x is equal to 30 plus y. Do you guys agree with me? That's really easy. And then I can substitute in 30 plus y right there for x. So I get 2 times the quantity. 30 plus y is equal to 5y. And that's an easy equation for you guys as long as you distribute well. And we just keep solving. I got y is equal to 20. And if you saw my work online and filled in notes, you can see that I end up getting like a negative y is equal to negative 20, y equals 20. I still end up solving for the same variable first. But what do I do to get the next one? Plug it in. Does it matter to me which equation you guys use? Which one are you guys going to use? The x minus y one? Okay. So I got x minus 20 is equal to 30. What's x going to equal? Great. Now, someone asked me, do I have to answer this as an ordered pair? The proper way, if we're going to talk about being proper mathematicians, yeah, you should. However, in the context of this problem, do I really need it as an ordered pair? Like, in context of the problem, we know it's 2 linear lines that help us figure that out. We made 2 linear equations. If you did it either way, I'd give you full credit. Now, if it was just a straight out systems of equations problem, where it's not with the geometry with it, would I expect an ordered pair? Yeah, context of the problem. All right, next one, my friends. It says find the value of x that makes the 2 lines parallel. All right, here's what's going to happen. Did everyone hear me on this?